Awesome. So my name is Karly Taylor. Thank you all so much for joining us today. I work for Activision Publishing.
And I'm David Durst. I'm a PhD at Stanford.
And we're here to talk to you today about hallucinations, and more specifically about how we've baited cheaters into self-identifying by reversing our detections. So let's talk a little bit about anti-cheat. I know a lot of you, how many of you in here make games or are game developers? Awesome, awesome. Keep your hands up if you work on anti-cheat. Or you don't want to identify yourself, I get it. We're all security-minded. I see you. All right. But working on anti-cheat, I tried to think of a lot of different analogies for what it feels like to work on anti-cheat. And this back and forth and kind of the cyclical nature of what we go through with combating cheating in online gaming. And what really stuck out to me was this idea of a cat and mouse cycle, where we, the anti-cheat developers, are the cats, more specifically Activision, and working on Ricochet anti-cheat. And the cheat developers are the mice. They're chewing up your cables, they're making nests in your walls, and you don't want them around, and it's up to you to find them. And so this cat and mouse cycle is something we're going to talk about in detail in the next few slides, because I really want everyone to understand kind of where we come from and the way that we approach problems. And there's one word I really want you all to focus on as we go through these next slides, and it's asymmetric. I want you to think of and imagine the asymmetry in the kind of problem that we're trying to solve, and keep that in the back of your head for what we're about to discuss next. So let's talk about the cycle. Where does the cycle start? Well, it starts where it always starts. We find someone doing something in our game that they shouldn't be doing, right? We see videos of it. We play the games ourselves, so we see it happening. And we realize, OK, there's some behavior going on that shouldn't be allowed in the game. So what do? Well, we gather our team of trusty engineers. We book a conference room. We drink a bunch of espresso. We stay up all night writing code, trying to figure out if we can figure out exactly what they're doing and what this behavior looks like. And we come up with a feature, right? A programmatic way to detect the bad behavior that we can actually deploy into our game. So then we all gather around, we put it through QA, we do all the testing, we make sure that it's going to catch the people we want, it's going to ignore the people we want it to ignore, and we deploy it into prod. And we sit back and we have a beer. We're in San Francisco, we have a kombucha. And we congratulate ourselves, and we're like, oh, thank goodness. We're going to buy ourselves at least a few weeks, right? And what do the cheat developers do? They change their behavior. And this is how the cycle goes, this detection cycle, and then the generation of changing behaviors on the cheat developer side. And round we go. So let's put this into an actual example, also an opportunity for me to show off some of David's amazing MS Paint art. So let's think about flickshot aimbots, right? Any of you who have played FPSs probably know what this looks like. An aimbot gives you the ability to move from opponent to opponent without actually having to do anything, right? You don't have to have any skill. You just kind of flick back and forth from opponent to opponent. So let's see here in our little stick drawing, we have a player unaware of their opponent behind them. For all intents and purposes, we can say they have no idea that they're behind them. But what you don't know is that the player is using a cheat. So what do? They turn on their flick shot, and they 180 no-scope the opponent behind them. They never stood a chance.
I feel like this happens to me all the time.
Yeah. I'm not very surprised. So what would a perfect flick shot detector look like, where you can catch this 180 no-scoping behavior? Well, I'm sure you all can think of a bunch of different things that this might look like. So pick your favorite one, and let's go back to the cycle. So what happens? Well, first, we start where we always do. We realize that this flick shot behavior is happening in the game, right? We detect that this is going on. So what do? Featureize a detection for these sus flicks. We deploy it into production. And then what immediately happens? The cheat developers add some jitter to their flick shot, and then the cycle starts all over again. And if you think I'm exhausted, I have makeup under my eyes, you can't see the bags under my eyes, it's because this goes on forever and ever and ever, right? So what does this really mean? And we spent a lot of time thinking about this. When I started in anti-cheat, this certainly was the way that we talked about this problem, right? Was you go round and round and round the cycle. And what you're doing every time you go around the cycle is you're forcing the cheat developers to change their behavior, right? And you hope that by forcing them to change their behavior 100 times, 1,000 times, 10,000 times, what are you doing every time? You're minimizing, oh my gosh, you're minimizing the available feature space for the cheat developers, right? Every time they have to change their behavior and be a little bit more human-like. And so you hope that there's this theoretical minimum, right? You're approaching this asymptote. You don't know where it is, but you're going somewhere where you're hoping that you will eventually force them to play more like humans, right? And the theoretical minimum and the goal of every anti-cheat is to eventually force them to play so human-like that they don't have an unfair advantage anymore, and that's when you can say that you finally won. And this is something that we spend a lot of time thinking about at Activision, obviously. As many of you probably know if you follow Call of Duty, we've had mitigations in our toolbox for a long time. And this is one way that we just try to increase the behavior generation costs for cheaters, right? When we find out that they're doing something, we deploy a mitigation like this one is my favorite, damage shield, which just puts a shield of protection around a victim so a cheater can't do damage to them, right? And it gives the victim a fair opportunity to fight the cheaters. And it forces cheaters to change their behavior. So if you want to learn more about mitigations, we have all of them online with examples, but I just wanted to highlight that, we focus a lot on this part of the problem, right? But as we were thinking about this cycle, we were like, all right, this is all well and good. And I think, the theory of minimizing the behavior space for cheaters is great, right? It's a really good idea. There's nothing wrong with it. But we like to think outside of the box. We like to get a little wild sometimes, right? So we thought, what if we didn't want to actually be the cat in this analogy? I'd say in most analogies, you probably don't want to be the mouse, right? There's not many times that that's actually preferable, but I think in this one, being the mouse is preferable because it's cheaper. It takes less time to just change your behavior than it does to come up with all of the detections. And this is where we will start. This idea, we don't even need to fill out the rest of the cycle, right? Because we know where it has to start. It starts where it always starts. With the cheat developers now as the cat, having to detect some sort of behavior that we're doing. So let's think about what this would look like in real life. And here it is, the name of the movie in the movie. Hallucinations. This is how we're going to reverse that cycle. These are fake players that look human to cheating players. So you can see here, what if you had this fake player, put it inside of a box? What's going to happen to non-cheating players? They're not going to notice it at all. What's going to happen to a cheating player? They're going to see it because they can see everything in the game. They're going to be like, hey, there's a person in that box. And you hope that they'll interact with it. And you can be like, that's a cheater. So let's talk about what a system like this would look like now that we have a vague idea of what we want to build. And what are going to be the constraints of this theoretical system were we to build it? Basic constraint number one. We just talked about this. Hallucinations need to look like real players in memory, right? If they don't look like real players, they're not going to fool anyone into thinking they're real players, and you're DOA. Number two, non-cheating players should not be able to observe the hallucinations, right? It wouldn't be good for us to think that everyone's a cheater if everyone could see it, right? It needs to be something that only cheaters can see and non-cheating players won't react to. And number three, just like everything we build, our implementation needs to be maintainable and performant, right? Same of any system, really. It just has to, it can't do anything it shouldn't be doing. It's going to be deployed on our servers, so it needs to be performant and it needs to be scalable. So you're probably thinking, Karly, I've been around the block a time or two. I've heard of this before. This isn't a new idea. And I would say, you're completely right, so thank you for coming to our talk. We'll see you afterward. But it's true. This has been around since Counter-Strike 1.6, at least variations of this idea. Most specifically, Lucia Hallucinations implemented something extremely similar, as did aimbot detection. And you'll see David's stick figure drawing again here. We want to revisit this. He will be selling prints after the talk. He'll be signing them. You can see the cheating player reacting to the hallucination inside of the box. Now, David, can you tell me what you think would happen if this was implemented IRL?
Wouldn't the cheat developers just ignore stuff inside boxes?
Oh my God, that's exactly what they did. They were just like, all right, don't look inside boxes anymore, y'all. Problem solved. So that's exactly what happened, right? When you implement this sort of static behavior, remember, the part of the cycle that we're aiming for is the change behavior part. So if your implementation is static, you end up in a situation where they filter it out and you're done. All your hard work is gone. So this brings us back to our constraints, and we need to add another one. Our basic constraints aren't enough. What we need to implement is that our hallucinations need to be configurable, and they need to be something where we can actually change the behavior. So our hallucination mechanism needs to support this configurable in-game behavior for us to keep it alive, basically. So now we're back. We know what's going to go in each part of the cycle. We know exactly how this is going to play out. Cheat developers are going to detect our hallucinations, right? If I was worried about this, I wouldn't be up here telling the public about it, right? Like I would be at home guarding this with my life. And it's okay. That's part of the system, right? We anticipate that they'll detect this, and that's okay. Because what are they going to do? They're going to have to featurize a detection. You know, they're going to have to gather their engineers. They're going to come together. They're going to say, okay, how are we going to filter out everything inside of boxes? It's not the hardest problem you've ever solved, but it is a problem to solve, right? They'll come up with a feature that they feel good about. They'll deploy a detection. They'll go to their customers. They'll say, hey, guys, you don't have to worry about those annoying fake players anymore. We filtered them out. You're good to go. Go rage. Have fun. And then what are we going to do? We're going to just change our behavior. And we're going to kick them back to the start of the cycle where they have to detect what we're doing again. And it's with that that I will hand it over to my esteemed colleague, David, to talk about how we actually implemented this in Call of Duty.
I'm going to try not to fall over. OK. Thank you, everyone. So now we're going to look at the design decisions we made in our implementation in order to satisfy these constraints. As far as hallucinations are concerned, there are 4 steps necessary to produce one frame of COD. Our first question is, when during these steps are we going to create the hallucination effect? The first step is running the game logic. Here we're going to update the server state, like where players are running, where they're shooting, and the status of any objectives. We cannot modify the server state when we create the hallucination effect. Otherwise, we might introduce bugs in the game logic. For example, consider a possible implementation of hallucinations as invisible, unkillable bots attached to a particular team. That team can no longer be eliminated, and so game modes that rely on team elimination, like Battle Royale, won't work. Karly, how upset do you think our streamers will be if they can't win anymore?
I think they'd be pretty upset.
I think so. So the next step is that we create the snapshot. Here, what we're trying to do is we need to serialize the game state into a data structure that can be communicated to the clients. As far as this presentation is concerned, you can just think of the snapshot as a list of player data. In our particular example, we have a single player in the snapshot, player A, and they've been allocated slot 0. The rest of the snapshot is empty because they're the only player in the server. The clients receive the snapshot and process it to bring their copy of the state up to date with the servers. At the moment that the real human players exist in client memory, the hallucinations also must exist in client memory. Otherwise, it would be trivial for cheat developers to tell what's real and what's fake just by looking at memory. Finally, the clients have to render the frame. The hallucinations cannot appear in the rendered image. Otherwise, non-cheating players will see them and react to them. Now that we've seen this cycle, let's use the process of elimination to remove all the parts that we can't actually use. We clearly can't change the game logic, lest we introduce bugs. And we also can't do anything on the client, because if we add functions for managing hallucinations on the client, the cheat developers will just lock onto them and trivially filter them out. By process elimination, this only leaves when we create the snapshot. The snapshot is wonderful from a timing perspective because it's created after the server state has been finalized, so we can modify it without introducing bugs, but before any information has been communicated to the clients. So if we modify it, the clients will have a hard time figuring it out. OK, so we know we need to modify the snapshot. The next question is, how are we going to modify it? When we started this project, what we thought was the simplest approach was just to modify it in place. We have a human-looking player already there. Sorry, we have a human player already there. And we can just change their properties in the snapshot to create the hallucination of the human. This looks great because it looks real in memory. But Karly, it seems like there's something missing in this snapshot.
What happened to player A?
Exactly. Player A is missing. So if we still want all of our non-cheating players to receive player A, we now need 2 copies of the snapshot. One with the hallucination of player A, and one with the actual player A. If you scale this up to a battle royale game where you might have 100+ players and multiple possible cheaters, you now might need to keep multiple different copies of the snapshot around, and we found that this violated our maintainability constraint. Of course, prior implementations did consider this approach, and you can implement it this way, but we didn't want this level of complexity. What we instead went with was a copy and update approach, where every snapshot, we generate the hallucination effect by finding a source player and finding a free slot in the snapshot. And we copy the source player to the free slot and then modify it. We went with this approach because it satisfied our constraints. 1, this looks real in memory. It's a copy of a real player. 2, non-cheating players won't notice it because we're not going to introduce bugs in the server state, and we're going to hide this hallucination behind a wall or some other way that disguises it from the renderer. 3, it's efficient because we're just doing a simple copy, and maintainable because we don't need many copies of the snapshot. And 4, the most important part, we have configurability. Since every snapshot, so every time we communicate with the clients, we are creating this copy, we can update its parameters, like its view angle, position, and animation state, just like you might do for a bot. And this means you can generate a range of behaviors, starting with simple ones that we've deployed today and we feel comfortable with, and leading up to more complex ones that more closely imitate how humans play the game that we have prototypes of. And remember, as we go round and round this cycle of generation and detection, we're going to need to ramp up to these more complex, more human-like behaviors. Let's look at some examples of these behaviors. We'll start with the simple ones that we deployed, and we'll get our way to the prototype. The simplest behavior we could come up with was let's just shove the hallucination right in front of a suspected cheater and let them deal with it. And so what we did here is we have a hallucinate. We're watching from the perspective of someone who's possibly cheating. And we're just putting the hallucination right in front of them. They look to the right, the hallucination goes to the right. They look to the left, the hallucination goes to the left. This is really wonderful for a demonstration where I don't think any of you have an IRL wall hack, but we are going to need to hide this from the renderer. So what we might do there is we might shove it off so far in the distance that it's beyond max draw distance and only visible to people who are using techniques other than a renderer to view it. And there it goes, so far off in the distance. Now, this is a simple technique. We deployed it, but we expect that this will last about as long as mayonnaise in the hot sun. Cheat developers are going to figure out to ignore the thing right under their crosshair. So a little bit more complicated of a behavior is to stick the hallucination at different angles relative to the possible cheater. To the right, to the left, or always behind. And so here what we're doing is we're going to shove the hallucination always behind them, and they're going to turn round and round, and they'll never see it. Their cheat radar will tell them they're about to die, but they can't actually see it. And please ignore the human you do see in this presentation. That's not the hallucination. That's an extra player for a later test. Okay. So the last part we get to is the prototype of the future. And this is where we want to make our hallucination look as similar to another human in the server as possible. So we make it as hard as possible for the cheat developers to tell what's real and what's fake. We might, in this future world, randomize some snapshot positions. And what we really want to do in the in-game world is we want to spawn the hallucination inside of another human in the server so that you can't tell based on initial position what's real and what's fake. Then we need a behavior generator to generate a trajectory for the hallucination through the world that seems human-like but differs from that real player. It'll then be up to the cheat developers to guess, based on the trajectory, what's real and what's fake. Our trajectory right now is very simple because this is a prototype, but over time we'll need to work on better and better trajectories. So there we spawn them inside each other, and we have our very, very basic emergence trajectory. So this is a wonderful long-term vision. But before we get there, we have to verify a short-term assumption. We have to make sure that our hallucinations actually look real in memory. Otherwise, no one's going to bother with this behavior nonsense. They're just going to look at memory. And so we verified that our hallucinations look real in memory by testing them against multiple implementations and combinations of common cheating techniques. And since all these implementations and combinations treated our hallucinations as if they're real players, we have a fair degree of confidence that they look real in memory. Please note, the following videos contain no actual cheat hallucination combinations. These are recreations of internal tests that have been designed for public release. So this most basic test that we're going to start with is a combination of an ESP feature, which shows our hallucination through the wall, and an aimbot, which locks on to the hallucination as soon as the player aims down their sight, thus treating it just like a human. Oh, sorry. The other test we're going to show you today is a more realistic example where we add in what's called a field of view filter. Here, we have the ESP, which shows the hallucination through the wall, and we have the aimbot, which locks on. But to prevent overly blatant lock-ons, we have a field of view filter, which disables the aimbot unless the target is within a certain distance of the crosshair. And just like a normal human, the lock-on only happens when the hallucination is close enough. Wonderful. So short-term problem has been addressed. We're fairly confident that our hallucinations look real in memory. Let's go back to the long-term vision. Round and round the cycle of generation and detection we go. And as we go around this, our new goal for anti-cheat, is for anti-cheat developers to create hallucinations which imitate how humans play the game. We can start with basic imitations, but over time, we'll need to get better and better imitations. And we want to do this because we believe it's easier to solve the behavior generation problem than it is to solve the behavior detection problem. Now, let's think about this goal a little bit more. We want autonomous agents that imitate how humans play the game. I've heard this idea before. These are bots. Hallucinations are just bots for anti-cheat. We want to reduce the problem of anti-cheat to the problem of bot design. Because if you can create a bot controller that imitates how a human plays the game, then you can create hallucinations that imitate how humans play the game. And if you have hallucinations that imitate how humans play the game, then you can make it challenging for cheat developers to detect it, and you can trick cheating players into reacting to them and self-identifying. Now, this idea of reducing problems to human behavior imitation is a core tenet of my thesis. I found that not only anti-cheat, but other problems in gaming, like human behavior analytics, also reduce to this problem, or may reduce to this problem. And so if you're interested in some ideas for how to imitate human behavior and some research, check out my blog. Thank you. Any questions? Oh, sorry. Please go to the microphone, too. Oh, there's a microphone behind you, so that all the people watching the recording can hear.
So if I'm if I understand this correctly, based on the constraints, it has to look the same in memory. I'm assuming probably same in GPU. You probably can't have a bot that actually runs into say close range combat, right? Like something in the doors. So those constraints exist. Is that right? Because it technically should be a renderable object, right?
It has to be a renderable. Yeah, it has to look real at the point. So if it becomes visible in the renderer, cheating players would react to it. But if it's always behind a door, it can look real. If it's always behind a wall or behind a door or somewhere where a human might be, but just the current player who's watching it can't see it, then it can look real in memory, but the GPU won't show it.
Oh, you're saying so the GPU doesn't show you?
No. Oh, sorry. We want to take a human behind a wall.
Yeah.
Oh,
I see. Yeah. Okay. So, I think I understand that. That's okay. So basically, if cheat makers are aware of your constraints, they can start designing cheats that are more within the constraints. So, for example, if you're doing aimbot, and then if you somehow have tech that can scan your GPU and recreate 3D structures, and then aim for you only when stuff isn't occluded, you could technically still do this, but obviously that's a ton more work, etc. And then does this also mean that if you're sending snapshots from the server, if you have a connection interruption, then because you're not updating the fake player, you could still potentially see them as a legitimate player for a brief moment because of that connection interruption?
If you choose the approach of shove them behind them, and they stop and they can turn around, and yeah, if you have client-side prediction, which enables you to turn around, and the other person gets stuck behind them, then you could potentially turn around fast enough to see them for a brief minute.
Okay.
The shove them behind them is a current behavior. We would like to build our way up to better things like behind a wall or things that don't enable you to turn around in 100 milliseconds.
Yeah. Cool. Yeah. Thank you. That's all.
Related question: when you're talking about occluding them so they're not drawn, so how do you spawn them in at the very start so that the cheat knows they're there but then also have them occluded in the future? How does that work?
Yeah, so you can limit which, so you're obviously not going to send them to all the players, because if you send them to all the players, some part of the map will always be visible to someone. So you're only going to send this to the person you think is cheating. And then, you have a PVS or something like that to help you figure out what parts of the map are not visible to that person. Now, of course, when you start sending an extra entity, the cheat will very clearly figure out, hey, there's a new entity that appeared, something's not right here. That's the trick of why we want to do something like spawn it inside, is to do something, and not done yet, but the vision is randomize your snapshot layout and spawn it inside another human so that so it has to start playing a guessing game. Your goal is not to beat the cheats, but to make a hard guessing game for them to solve.
And so then sort of a related question to, you can send the sort of updated state information only to the people you think are cheating.
Yes.
Is that done in like a dynamic sort of way where the system is able to tell, oh, I think this might be a cheater, like let's spawn a hallucination for them, and then it's flagged, that account is flagged later if they respond to that hallucination? Like how dynamic and automatic is the end-to-end process?
Yeah, the whole thing is automated, so that's a great question. Basically, any person that you think is suspicious, right, the idea is to spawn this close to them behind some sort of geometry, like David said, using the PBS, and see if they react to it, right? So it's like almost like a final detection method almost. Like you're suspicious, and that's like the nail in the coffin, right? And it's also confusing to them and funny.
Cool. Thanks very much.
So I just like to emphasize, like I can't say, like the randomization is not implemented today. It's just.
Hi, thank you for a great panel. So I work at Act Defense. We help trust and safety teams dealing with adversaries, and that's kind of what cheating is. It's an adversary that's hurting the trust in the game. And what we do for primarily social media streaming kind of content platforms is the same that cyber threat intelligence team do for SOC and security teams, which is listening to the bad guys, right? And I've not seen that approach in gaming in terms of shortening that cat and mouse game, especially around the detection of a new cheat, as well as detecting when the cheat creators have detected your change of behavior. Shortening that cycle, I guess, also a method of improving the cat and mouse game. Has that been tried? I've not seen it too much in gaming. Your thoughts on that?
I don't think that we want to specifically talk about anything in that realm right now.
Understandable. That's why
I'm
we
already
can't talk about our
telling y'all a
customers.
lot. Come on.
All right. Thank you. That's
You're
enough.
welcome. Thank you for the question.
I just had a quick question. Like, how often do you accidentally ban players? Like, if a player is just firing and accidentally shoots into the wall and hits like a copy and they get banned.
So it's not like it's not, like one shot, you're done, right? Like we said, it's already someone that we think is suspicious. And so the whole idea behind things like this is that you want to show some sustained pattern of behavior. So no one thing is ever like the thing, right? Without some sort of like actual detection. So I'll just say that. These are all things, it's just information for us, right? It's data.
Gotcha. How does the system detect that someone might be cheating, though? Like, are people actually monitoring it, or is it like an AI model that's detecting it, or?
We have all sorts of systems, I'll say that. Thank you.
Yeah. Hi. Thanks for the great talk, by the way.
Yeah.
So what you presented, it sounds like a great solution for so-called rage cheaters, but the ones that are playing semi-legit cheating, they usually just use wall hacks, and they activate aimbot only on shoot within a very limited angle, so basically it sticks when they shoot. So my question is it possible to implement something server-side that would understand that the player is not visible and the server would not send the player data to the actual to the client, I mean. So only when it's within the viewport, the server would send the data, and this way it would eliminate wall hacks to a degree.
Yeah. So
I think that's been done, right?
So prior other games. So I can't talk specific which games, but there have certainly been FPS which use the PVS to limit information, and so they only send you items when they're within the PBS or within a certain distance. There are challenges there where you have to account for a variance in the network latency, because if you don't send someone a piece of information and there's a lag spike, they could run around the wall, not see someone, and have someone pop in. And so these are techniques that are implemented, and I believe are in production today. Not sure exactly which games, but but they do take some nuance to deal with the complexity of the network.
And think about the complexity, too, in terms of multiplayer games, right, like a traditional Counter-Strike type game versus a Battle Royale. So like map complexity and size certainly plays a huge role in something like that being feasible at scale.
And so last question would be, is it much harder to detect wall hacks rather than aimbots?
Different problems, I would say, for sure. And what you had originally said about the people who play legit, who just use this to where they can just get a little bit of extra information. Also, just think about how annoying it would be if you're trying to keep track and there's like suddenly 8-10 people behind the walls, right? Like even a little bit of impediment that makes it obnoxious to try to figure out who's real is a win to me.
Okay. Thank you.
I've heard you use the term PBS a couple of times. Does that have to do with like level geometry and visibility between spaces, or can you expand on that?
Pardon, I should expand on my, sorry, I shouldn't use opaque terminology. PBS is the potentially visible set. So what you do is you divide the map up into regions, and then given a single point in the map, you have a set of all the other points in the map that are potentially visible. So you could do something like take a nav, not the only way, but you could take a nav mesh, and for each point in the nav mesh, you could trace rays to all the other areas in the nav mesh. And now you've computed an approximate potentially visible set. Given how big your nav mesh is, and given how many rays you trace, this may be an approximation you trust to various degrees.
Okay. Well, lets you sort of pre-do the work that would be computationally way too expensive to do in real time on the server. And then is the fact that you're duplicating players, like, are you not worried about people saying, oh, well, there's 2 of this player right now, I'll just ignore both of them? Like, or, the fact that only one of the, have you considered just like teleporting a human player for a second while the cheater is potentially not seeing it, or is that just?
Well, I mean, who said you only have to do it once?
Okay, I see, and then they'll react. Anyway, but yeah, thank you for explaining the
Thank you.
visible set thing.
Yeah. Oh, sorry. I think we're going to, sorry, thank you guys. So we are out of time, unfortunately. Okay. We can continue to answer questions in the in outside or in the breakout room. Thank you very much.
Thank you, everyone.